Good morning. In this class, we'll discuss about slow frequency of spread spectrum. So, slow frequency of spread spectrum means several symbols are transmitted on each carrier hop or each carrier frequency. Let's say this is my one frequency of a carrier frequency. So, by using one carrier frequency, we are transmitting several number of symbols. So, such type of communication we are calling slow frequency of spread spectrum. As I'm saying, on each frequency of we are transmitting several symbols. So compared to op rate, symbol rate must be higher. So RS must be greater than RH. So RS is the symbol rate, which is 1 by TS. RH is the op rate, which is 1 by TC. With TS is the symbol duration. TC is the chip duration. So let's say RS is greater than RH. So RS is equals to N times the RH. So as we know, we are substituting the value of RS and RH. So RS is equals to 1 by TS, RH is equals to 1 by TC. So I can write TC is equals to N times TS if N is equals to 2. For example, we are transmitting for each symbol consists of 2 bits, for example. So TC is equals to 2 times TS, right? So in each chip duration, we are transmitting how many symbols? 2 symbols we are transmitting. So let us see what is the block diagram. The block diagram is same as that of previous case. So this is a block diagram for transmission, right? As I'm saying, binary data sequence I'm passing through the MRAFSK, right? And this data I'm giving to the mixer. Another input can be generated by using pseudo random sequence, right? I'm giving to the frequency synthesizer so that it can produce the carrier frequencies. Depending upon the combination, I can choose the high frequency or low frequency. We are transmitting here sum of the two frequencies as a FHSS. The same operation I'm using here. The only change is that I'm transmitting more number of symbol through the each frequency of. So let us consider k successive bits of the PN sequence. I'm taking k successive bits of the PN sequence so that the frequency synthesizer can produce the 2 to the power of k output frequencies. For example, let's say this is my PN sequence. This is my PN sequence. Now I'm taking k is equals to 3. K is equals to 3. So the PN sequence can be divided into 3 bits as one segment. So 001 is my one segment. I'm randomly choosing this PN sequence, right? 110 is another sequence. 001, 001, right? And 011, 001 is the segments. Now, as I'm using k successive bits to the frequency synthesizer, it can produce 2 to the power of k output frequencies. So here I'm taking k is equals to 3. So the input combination of PN sequences are 0002 to 111, right? Whenever I'm giving 00 combination through the frequency synthesizer, it produces one output frequency. Let it as FC0. This is my one carrier frequency. Similarly, 001 FC1, 010 FC2, and 111 FC7. So these are the carrier frequencies or output of the frequency synthesizer. So depending upon the input bit combination, the MRAFSK will produce the 4 different output frequencies. Let's say M is equals to 4. So 00 is one combination, 01 is another combination, 10 is another combination, 11 is another combination. These all are the combination of input symbols. So whenever I'm giving 00 here, it can produce F0 is the frequency, 01 F1, 10 F2, 11 F3. So these are the frequencies I'm giving here. So now we need to draw what is the hopping spectrum in the case of slow frequency of spread spectrum. Now this is one example for drawing the frequency of hopping spectrum for in the case of slow frequency of spread spectrum. So let's say randomly example, this is my binary data 01 10 11 11 0 10 00 10 01 11 10 10. This is my binary data. I'm taking 2 bits as one symbol, and this is my PN sequence, right? We know that we are using 3 bits as one segment. So I'm dividing, and each carrier frequency is transmitting 2 symbols. So this is my one frequency of or one carrier frequency, we are transmitting 2 symbols. 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 Now let's say, so this is my frequency axis, this is my time axis, where the time taken for each of, we are denoting it by TC. The time taken for each symbol, we are denoting it by TS. Right? So this is a 0 to TC is my one hop duration, right? So in this hop duration, what is the frequency I'm using here? 001. For 001, right? So 001, the carrier frequency is FC1, right? I'm using your FC1. So this is my FC0, right? FC0, and these all are the output frequencies of MRFSK, F0, F1, F2, F3, right? Again, FC1, I'm having 4 output frequencies of MRA, F0, F1, F2, F3. FC2, F0, F1, F2, F3. FC3, F0, F1, F2, F3. FC4, F0, F1, F2, F3. FC5, F0, F1, F2, F3. FC6, F0, F1, F2, F3. FC7, F0, F1, F2, F3. Right? So this is my frequencies on y-axis, and x-axis I'm taking time. Right? So during the first half, I'm using carrier frequency 001, which is my FC1 carrier frequency. FC1 carrier frequency. In this carrier frequency, I need to transmit 2 symbols. One symbol is 01. 01 can be represented by using a frequency called F1. Right? I'm using a F1. 11 I'm representing by using F3. Right? So what is the initial carrier frequency? FC1. So I'm going for FC1. Right? So what is the first frequency? F1. FC1. F1, I'm transmitting here, this is my frequency from 0 to TS, let's say TS. Now during another TS duration, I'm transmitting what is the frequency? F3 in the carrier frequency FC1. FC1, F3, so this is my carrier frequency. In the first half, I'm transmitting these 2 symbols. In the next half, the carrier frequency is FC6. I'm going for FC6, right? So one symbol is 11, FC6 plus F3. FC6 plus F3, I'm transmitting here, this is my symbol. FC6 plus F2, right? FC6 plus F2, this is my symbol in the next half duration. Similarly, like that, I need to draw all of frequencies. So this spectrum we are calling halving spectrum. This can happen at the transmitting end. At the receiving end, we need to de-halve. That means in the 0 to TS, what is the symbol we are transmitting? The symbol we are transmitting F1, right? Another duration, we are transmitting F3. So F1, F3, 1, that means F3. So like that, we need to draw the de-hopping. So this is the slow frequency of spread spectrum. Now we'll see what is the fast frequency of spread spectrum, right? So in the case of fast frequency of spread spectrum, right? So we'll transmit, right? We transmit only one symbol. We transmit only one symbol, right? Only one symbol by using multiple number of frequency ops, right? That means we are using more than one carrier frequency to transmit one symbol. Such a type of communication we are calling fast frequency of spread spectrum. As I'm using more number of one carrier frequency to transmit one symbol, the op rate may be higher than symbol rate. So RH is greater than RS. So let RH is equals to N into RS. So I'm writing, so I'm simplification. So TS is equals to N into TC. So for one symbol duration, I'm taking more than one carrier frequency. So this technique we are calling fast frequency of spread spectrum. So similarly, you can draw the hopping spectrum and de-hopping spectrum as reference to that of slow hopping frequency spread spectrum. Thank you.